Okay, so this is interesting. So now we have only 3 people in class. Okay, let's see. I'm gonna, okay. Let's see. So, so I did not mention looking at lecture videos, but did anyone go through the lecture notes or the lecture videos that we're discussing the rest of the topics from the this chapter, let's say. So we were talking about the multivariate normal distribution, right? And the idea was that we went through a couple of properties. And so do you hear me? Is it okay?
Yes.
Yeah, okay. So we had, let's see. Okay, someone else joined. Let's see if I can get a, okay, so did you guys get it? So let me just recap so that you guys can remember what we talked about. So we started talking about this multivariate normal distribution, which is an extension of let's say univariate scalar normal distribution. And we talked about a couple of properties. The main one is that if you have a multivariate normal distribution, then any affine transformation would have a multivariate normal distribution. And we went through an example here. And a consequence of this is that the marginal distributions are multivariate normal. For example, any subvector of the vector, for example, something like this, this is a subvector. This would be multivariate, will have a multivariate normal distribution and so on. And then the third property is that the conditional distributions are multivariate normal. And one property was left, which is this uncorrelatedness. So did any of you guys had a chance to go through this part of the recorded videos, or?
Yeah, a little bit, I think.
Okay. Anyone else? Max?
Yeah, I looked at it a little bit, not the whole thing though.
Okay. Byung-gu? Oh, so you probably can't talk. Okay. Anna, did you get a chance to go through it, or? Okay. So that's fine. So maybe one of you guys, Danny or Max, do you want to maybe help us go through this, or if you have any questions, maybe? What does this slide, let's say, what is it trying to say? Is it roughly?
I think it's basically trying to say that while what is it? Independence is always uncorrelated, but uncorrelated doesn't always mean that it's independent. That was what I wrote down from this slide.
Yes, so this is one of the important ideas. This is general. So what does the uncorrelatedness mean?
Like the two variables are not, like they have no covariance.
Yeah, the covariance is 0, basically.
Or correlation,
yeah, correlation or covariance is 0. And the correlation measures the linear dependence. So it means that they have no linear relation, but they could have some sort of nonlinear relation, and so they could be dependent. So independence is a little bit stronger. It's actually a lot more stronger. I'm gonna avoid giving the exact definition, maybe. So you can go and review what independence means from basic probability. So basically, so one way of stating it is that joint, let's say, densities factorized. So if I have two variables, y1 and y2, if I look at the joint density, let's say if they're, for example, multivariate normal, if I know that they're independent, then the density factorizes. So let's say, maybe just briefly mention independence. If y1 and y2 are independent and have density, say fxy, xy, then the density factorizes. You would get f of xy, x. You get it, it's a product of the marginal densities. That's one way of characterizing it. Equivalently, you can say the probability that x belongs to a set A and y belongs to a set B can be written as the product of the probabilities for any set A and a set B. So this is usually how it's defined, and then in the cases where you have densities, it translates to the density factorizing. This is basically a infinitesimal version of that.
Professor?
Yeah.
Just for clarification, do you mean probability of y part of
Yes,
B?
yes. Thank you. Yeah, that's what I mean. And these are equivalent. And then another thing that I'm going to add here is that independence is equivalent to expectation of, let's say, f, or let's say, I can write this as covariance of f of x and g of y. These have to be x and y, basically. Sorry. I mean x and y. Not, so you have two random variables, x and y. So this is a little bit advanced, but independence is equivalent to saying that the covariance of f of x and g of y is 0 for any, basically, function. Any functions, let's say f and g. Here there's like the qualification, any measurable function. Later on, if you continue with probability and statistics, you'd get into measured theoretic probability, and you'd, I'm not going to explain what measurable is here, but just add it to be correct. If you take a measured theoretic probability course, you would learn about measurability and what measurable functions are. Basically, they're any sort of reasonable function that you can think of is measurable. So this is going to be equivalent. So and you can see, so sort of uncorrelatedness is equivalent to covariance of xy, or it's defined actually. This one is defined as this being 0. And you can see this is a much stronger assumption. So this, if this only holds for f of x equal x and g of y equal y, only the identity functions, then you'd have uncorrelatedness. But independence guarantees that basically any function of x is independent of any function of y. This you can expand, is equivalent to expectation of f of x, g of y is equal to expectation of f of x. Okay, so this is a rather advanced view of independence, but if you like understand this a little bit, you would see exactly how different they are. So independence is much more stronger. So it guarantees that any nonlinear function of one is independently or uncorrelated from the other. So they don't have a relation in a very strong sense. Yeah, we can go into this, but because this is not a probability course, I'm gonna stop here. Is this clear, sort of, to some extent?
Yes.
Yes.
Yeah,
Okay.
it's
Okay. So what this slide is trying to say is that these two concepts, although very different, not very different, but quite different. So from this, you can see that independence implies uncorrelatedness. But the other way around in general is not true. True in general. However, in the MVM family, the reverse direction is true. What this means is that if you have a vector, let's say if the pair of random variable, if this has a multivariate normal distribution, and if they're uncorrelated, it basically means that these elements are 0 in the covariance matrix, then you can immediately conclude that they're also independent, which is a very strong property. So y1 and y2 are independent if and only if the covariance is 0. And this is very useful because establishing independence in general is not that easy. So you can see from this, if you want to show it, you have to somehow argue that the covariance of any function of x is independent from any function of y. Or actually you have to, I mean, it's equivalent to showing that the density is factorized. And okay, so this has to hold. And for example, you can verify that this is the case. So you know the density of the multivariate normal distribution. So you can try it for two random variables. Assume that y is y1 and y2, and assume that covariance is 0, and then show that this density factorizes. You can write it as a function of y1 multiplied by a function of y2, and that's enough. So, I mean, this has to be densities, but you can also argue that as long as it factorizes, it's fine. So you don't have to necessarily establish that the pieces are marginal densities, as long as you can write it as, let's say, u of x times v of y, without verifying that these are densities. That's okay, because then you can normalize them to be densities. So as long as you can write the joint density as a product of two univariate functions, one a function of x only, the other a function of y only, then that would be enough. And so you can verify this and establish this property for yourself. Okay. So this also, saying this also follows from lemma 2. Okay, so from this is also follows. That's another way of saying it. Anyone knows how independence can be characterized? There's an equivalent characterization in terms of conditional distributions. Did you get a chance to go through that part of the lecture? How we can use, this is another way of showing that this property holds. So if I have two random variables and I compute the joint distribution, sorry, the conditional distribution, let's say y1 given y2, what would have to happen to this conditional distribution for me to conclude that y1 and y2 are independent?
Professor?
Yeah.
Would the conditional distribution just be the marginal of y1?
Yes, that's exactly what will happen. Another way of saying it is that you want the conditional distribution of y1 given y2 to be not functionally dependent on y2. We don't want y2 to appear anywhere. So you can see this is in general normal. multivariate normal, and the covariance is independent of y2, doesn't functionally depend on y2, but the mean depends on y2 through this term. And if I can enforce a condition such that this term is 0, then this mean is going to be the same as the preconditioning, like the marginal mean. And so I would get independence, and this is exactly going to happen if sigma 1, 2 is 0. Okay, so if sigma 1, 2 is 0, this whole term is going to be vanishing. And if it's not, then you can argue that this is not going to be 0 for sure. And so the mean would depend on y2. So we get a distribution here that's independent of y2 functionally, if and only if sigma 1, 2 is 0. And then you can also verify that this distribution exactly would be the marginal, because in that case, I get this mean and this covariance matrix, and these are the marginal mean and covariance. So either statement is good. So if you do the conditioning and you see that the conditional distribution of y1 given y2 is the marginal distribution of y1, you're good. Even if you don't know the marginal distribution of y1, as long as you see that the conditional distribution does not depend on y2, in the sense that if I vary y2, the conditional distribution doesn't change, you see independence. So there's a very natural idea, so like geometric interpretation of relation.
Professor, I have a quick question.
Yeah.
So is that saying that always in the MVN, the sigma 1, 2 is always 0? Like it's always uncorrelated? Is that like a general thing?
Can you say that again?
So scroll down a little bit.
Down or up?
Down, yeah.
Where?
So where it says, however, in the MVN,
Down.
the reverse is true, like right there.
Yes, the reverse, okay, so can you complete your sentence? Maybe.
Yeah, no, I was just curious as to if like sigma 1, 2 is always 0 for an MVN.
No. That's not what this means. Sigma 1, 2 can be any valid, sigma 1, 2 can be anything that makes this positive semi-definite. So any valid covariance matrix can go there. So what does this mean? Maybe someone else wants to chip in. So what do you mean? What do I mean by saying that the reverse direction is true?
Well, no, I know what it means. I was just curious as to like why that is the case. Like,
That's what I was trying to argue. So
okay, yeah.
Go ahead. So this statement is not saying that we always have uncorrelatedness. This is a conditional statement. If you have two random variables that are multivariate, normally distributed, and you know that they're uncorrelated, then you can conclude that they're independent, right? This is not saying that every pair of random variables that is multivariate, normally distributed are uncorrelated, right?
Okay, I see.
There's a difference, right? Yeah, and then the argument why this is true, that's exactly what I was trying to say. There are multiple ways. One is to show that if they're uncorrelated, so the density factorizes if and only if the sigma 1, 2 is 0. Whenever this is 0, the density factorizes, and if the density factorizes, this is 0. Another way is to see that this conditional distribution does not depend on y2 if and only if sigma 1, 2 is 0. Both of these are good ways of seeing this. Yeah, maybe I'll forego the geometric interpretation because it's a little bit tricky, and if we get a chance, maybe, or if you're really interested, we can talk about this in the office hours. But this is good enough, I think. This is this can be proved in multiple ways, and the end result is simple. So if you know that you're in the MVN family, and if you have two pieces of this multivariate normal distribution, two you partition the vector into two pieces. So these two could be coordinates or could be actually two pieces of the vector that are of size larger than one, basically. So you could basically partition the vector into any two pieces and then ask whether this piece is independent of that piece. And there's this cross covariance, sometimes called cross covariance matrix, which is this submatrix in sigma. And if that whole submatrix is 0, then you can conclude that these two pieces are uncorrelated. And by this result, they're going to have to be independent as well. Okay. So this is a fairly strong and interesting result that allows you to verify multiple such sort of relations. So suppose, for example, let me give you an example. So we had some problematic. Remember this example that we had here. It was problem. And did anyone go through this and figure out whether this was the correct, like a valid covariance matrix or not? We had some contradictory conclusions towards the end of the previous lecture, and we decided maybe this is not a valid covariance matrix. Do you get a chance to verify it, or?
Wait, how will we verify this, Professor?
So this is the question that's here. So verify that this is a valid covariance matrix. How do you verify it? This is the answer, right? So you have to verify that this is positive semi-definite. It's going to be a covariance matrix if and only if it's positive semi-definite. It's a valid covariance matrix if and only if it's positive semi-definite. Okay? Does that make sense?
Yeah, so does that mean that we should put it into the spectral decomposition form and then check whether the middle term is semi-definite or it's greater or equal to 0?
That's one way. Equivalently, you can just compute the eigenvalues and verify that all of them are non-negative. That's okay. The approach.
Yes.
Another approach is using this idea. It seems like people have forgotten about the last lecture. So there is another characterization. So one is all the eigenvalues are non-negative. The other one is that all the principal submatrices are have non-negative determinants. So principal submatrices are the matrices that you get. For example, these are principal 1x1 submatrices. These are principal submatrices. These two are and this one are 2x2 principal submatrices, and the 3x3 principal submatrix is just basically the whole matrix. All these determinants have to be non-negative. If you verify that, that's equivalent. So this is these two are equivalent. So it's up to you. You can compute the eigenvalues or you can compute these determinants. Okay, so try this for yourself. Try to verify whether this is PST or not. It's a good exercise. I'm gonna do this, but let's say change it a little bit instead of assuming that that's the correct matrix. So I'm gonna do like 4 minus 4. I guess this was 2. Is it 2? No, it was 1. Okay. 1. Yeah, I'm gonna do 2, so it's fine. So I'm gonna do like 2 here. Let's say 1/2 here, and 0. Okay, so we have y1, y2, y3. Normal, which means 0, 0, 0, and covariance, and this covariance. So what kind of independence on correlatedness relation I can get from this?
Professor,
Yeah.
we get that y1 and y3 are independent because
Yeah.
they are NBN and they have zero covariance.
Yes. So y1 and y3, the covariance is here, so they're independent because they're uncorrelated and we're in the MVN. So this is what so this means independent. Okay, so how about, let's say y1, y2, and y3. Can I conclude that they're independent?
No, because they have covariances.
They have non-zero covariance, yeah, so that's exactly it. So this is the covariance or cross covariance between y1, y2, and y3. So you can just look at one of them. And so this can't be true. Okay, so not independent. So how about, for example, this? So if we have instead 4, -1, -1, 2, 0, 0, 2, 0, 0. How about this example? Would they be independent in that case? Can I conclude y2, y3 is independent?
Yeah.
Yes, because then this is 0, so they have to be independent. Yes. And this is basically the largest independence, like partition into two pieces that you can get. You can also, for example, get that y1 is independent of y3, or y2 is independent of y3. But this is, these all follow from this. And you can also read it off the covariance matrix. Okay, questions, comments? If not, then we can move on. This slide is about something related to whitening, which I'm going to skip, and you can go over this yourself in the lecture, the previous recorded lectures. And if you have questions, let me know. It should be quite easy to understand once you go back to the whitening and combine it with the properties of multivariate normal distribution. This gives you a nice recap and some interesting results of what whitening does in the context of multivariate normal distribution. We talked about multivariate normal distributions, and we talked about decorrelation or whitening, and this slide combines the two. And it would be good for you to go over it yourself and try to figure it out. Okay, any question about anything in the multivariate normal chapter, let's say? So we're done almost with it. So let me recap and then move on. So we have the definition of the multivariate normal distribution, Y are the density. It's characterized by a covariance matrix and a mean vector. This density form we usually don't use in this course, but we use the properties that are derived from it. The most important one is that affine transformations of a multivariate normal random variable are again multivariate normal. So you can say the multivariate normal family is invariant under affine transformation. So if you do affine transformations, you don't leave the family, you're still going to be in the family of multivariate normal distributions. The second one is that the marginal distributions are multivariate normal. And the third one is the conditional distributions are multivariate normal. And the last one is that uncorrelatedness is equivalent to independence. So these are the four important properties that we need for multivariate normal distribution. Okay, any question at all about any of this? Maybe give you a few seconds to think, and then I'm going to try to, in the meantime, go over and find the next set of slides. Okay, so these are not necessarily good for so any questions? Okay, seems like people are okay with moving on. So let's move on to the main chapter basically of the course, which is the discussion of linear models, and in particular the multiple linear regression model. So anyone got a chance of looking at this series of lectures? Did you get this far? Anyone? No? Okay. So it seems like we have to go through this. So I encourage you to go through the recorded lecture videos for this. I'm going to talk a little bit about it. But maybe I should first ask, did people learn about multiple linear regression in previous courses?
Yeah.
Yeah, okay. So what is it? You wanna?
I mean, it's a way to predict like a response variable using other, as it says, like independent, like regressive variables to kind of like create an equation to like predict something.
Okay, that's good. Anyone else have any other idea about what multiple linear regression is? So the idea is to predict a response given a set of independent random variables. Is that the general idea? So where does the linear part come in, or multiple linear regression?
Because like all of the variables are being added together. That's why it's linear. There's no, it's not like a logarithm or something like that, I think. Might be wrong.
Okay, I see. Okay, okay. Yeah, that's more or less it. Anything else about the why it's called multiple?
There's more explanatory variables for this response, and the correlation between each response, each explanatory and response is a linear relationship.
Okay, yeah. So the multiple part is because you have multiple, let's say, explanatory variables. So let me just maybe briefly mention. So the best way to understand what this is that, let's say, multiple linear regression is a model. Okay, this is a model for a response variable, or let's say a model that relates a response variable to a set of, let's say, independent. Independent is not a good name because it just, there are too many things called independent. So explanatory variables. These are all names, or covariates usually. Statisticians call them covariates. So a bunch of other variables that are assumed to vary on their own, and this response is somehow assumed to be dependent on them. Response variable is sometimes called dependent variable. So it's just a model that relates these two, okay, in some way, and it's let's say a stochastic model. So there is some noise in it. So the best way to understand it is just one model for your observations. And the way this model works is that if I have, let's say, my response, in general, I can write it as, let's say, a function of x1 up to xp. These are my independent variables. Usually you would add a little bit of noise. This would be my noise. So this would be, usually these are assumed to be deterministic, whereas this f is assumed, sorry, this epsilon is assumed to be random. So this is modeling y as a function of x1 up to xp and some noise. So this is scalar. This is reals. And I usually, for example, in this course, we write this as a vector, x1 up to xp. And then I can write y as a function of this x vector plus epsilon. So this is a general regression model. We're regressing y on x. Basically, we're trying to explain y as a function of x plus some noise. General regression model. And if you want, multiple. So a linear regression model, assumes that this function is linear. This f is a linear function. So you remember that we talked about linear functions and affine functions. You remember what an affine function was? So linear function is a special case of affine function. So this is the same notion of linearity. So a linear function, if it's a linear function, I can write it as a matrix, which in this case would be a vector beta transpose times x. Okay, because this is univariate, so the output is in R, the input is in RP, p-dimensional vector, and a linear function generally can be written as a matrix times the input, and this matrix has to be 1 by p, so I can represent it as a vector. So it includes the ideas that you had that things add up, but you're also scaling them. So you scale the coordinates and then add them up. So that's a general linear function of a vector. So if you make this function more complicated, you get more complicated regression models. But that's the basic idea. So this is a general linear function of x. So linear function means f of, let's say, x plus y is equal to f of x plus f of y, and f of, let's say, alpha x, where this is a scalar. If you add up two vectors, the f is added, and this is going to be alpha f of x. That's what the linear function means. And so you can verify that this function satisfies those, and in fact, you can show that any linear function can be written in this fashion. So this is a more general way of viewing multiple linear regression. And so multiple linear regression is the following model. Y is beta transpose x plus epsilon. Okay, so epsilon is not random here. Beta is random. Beta is not random generally. Beta is a coefficient vector that you would like to estimate. And x is collects these covariates. Okay, and the inner product is so this you can also think of as the inner product. If you remember what the inner product was, it's just the inner product of beta and x. So you represent the response as the inner product of beta and your independent variables plus some noise. So this is noise, or if you want, error, which is random. So this is random. This is generally non-random, although you can assume it to be random. This is also non-random, and this is going to be random. So it's a random variable. Okay, so that's the easy way, I would say a fairly general way of understanding what multiple linear regression. Okay. So you start from a model that tries to model your response or independent variables as a function of your covariate vector. And you can write this in general as a general function of x, y is general function of x, and you would, if you assume that there is an additive noise, so that there is some perturbation unknown added to it, then you get a general regression model. And then what you can do is assume further that f is a linear function. And so it has to be like this. Then you can write the model like this, okay? This is a compact way of writing a linear regression model. Okay, sounds good. Everyone on board?
Yes, sounds good.
Yes, no
Yep.
question. Okay, so then what you would do is that this is sort of that's called the population level model. In practice, you would sample from this model. So you repeatedly get, let's say y1 equal beta transpose x1. This is the first patient or first subject, and then you get y2 beta transpose x2. This is another guy, 2, and then you get up to yn beta transpose xn plus epsilon n. So I have n subjects or people, or I don't know what units of measurement. So let me try to change this to, okay, so I get this, and then compactly I can write this as yi is equal to beta transpose. This is again a vector that collects all the covariates of the ith guy plus epsilon I. So I from 1 to n. And these are independent draws from the population model. From this. So for everyone, we get a random variable y and a vector x that has the covariates, and there's a corresponding random noise. Okay, so that's the sampled version, let's say. Sampled version, which we usually work with. And if you understand this, then you can also write this more compactly as y1, y2, y3. Maybe I should give myself more space, sorry. Do this, come back here. I have another page. This did not work. Back. Okay, so this is good. So we can write this up to yn. I can put them here, and then I get beta transpose. You can also write this as, can I write this as xi transpose beta? Is that valid if I do this?
No, because that's different dimension.
So what are the dimensions here? So xi is in what dimension? Xi is p by 1. Xi is a version of this. So if I want to write this, so xi basically would be xi1, xi2 up to xi p. Okay, I don't know if this is visible. Maybe I should do it. Dimensions. Try this down. Oh, okay. So dimensions. So xi is xi1, xi2. So these, every subject has p covariates. So this is a vector in Rp, okay, n by p, so p by 1. And beta is the same, so it's going to be beta 1, beta 2 up to beta p. This is in Rp, and so it's p by 1. So what is the dimension of beta transpose xi?
That'd be 1 by 1.
This is going to be 1 by 1. How about xi transpose beta?
Also 1 by 1, yeah.
Okay, so now can I do that? Can I set them equal?
Yes.
Yes, you can set them equal because this is 1 by 1. Basically, you can take the transpose of this. The transpose would switch the order and transpose each element. And the transpose of a scalar is the same as itself. So once you transpose it, it has to be the same as itself. And the transpose is this. So they're equal. Or you can just expand it. Just expand that. Both of them are basically the product of individual entries here and then add it up. So they're the same thing. So I'm going to write this that way. That's easier. Xi transpose, sorry, x1. This is the first vector times beta, x2 transpose times beta up to xn transpose times beta, and plus epsilon 1 up to epsilon n. So 2, okay. And then if you go back to some of the earlier linear algebra discussions, you can verify for yourself that this is equivalent to just writing it like this. I can pull beta out because this is a row vector. And when I multiply it, this row gets multiplied by this column. And this gives me the first row. And then the second row gives me the second row of this, and so on. So I can do this. And the other one is going to be as before. And this one just would be y1, yn. So we now call this y. This is now the vector y. And then I'm going to call this x, capital X. And the beta is itself beta. And this is going to be vector epsilon. So I can write this in matrix vector format in this neat, compact way. And this is just an n by p matrix. This is p by 1. This is n by 1. And this is n by 1. Okay. So this is the vector form of the sampled version of the linear regression model, where we now collect the data on n samples and p covariates. Okay, sounds good?
Yes.
Okay, have you seen this sort of equation or this way of writing multiple linear regression?
Yeah, I think so. Maybe I think 100B.
100B, okay. Max, did you see this?
Yeah, I think 100B, and then also in like the 101 series, they do this too.
Okay, so this sort of a matrix format is familiar.
Oh, well, not the matrix format, but like the general format.
General idea. Okay.
Yeah.
Okay. So this matrix form, if you haven't seen it, or you can go back to your previous courses and see if you encountered this. This is very useful way of is a very useful way of representing multiple linear regression. And this is going to be all basic sort of formula that we work with, that a lot of things follow from this. And so it's useful to for you to go through this derivation, also do it in the recorded lectures in a slightly different fashion. But how you start from, so this is the population version, this is a single version of things, and then you sample this, you get this version, and then you can write this compactly in this fashion, and then we work with this. And you can see why we spend a lot of time talking about random vectors or matrices. So this is a random vector. This part is a deterministic vector for us. And so this is going to be a random vector. So it has a, for example, mean vector, and it has a covariance matrix. And I can assume, for example, that this epsilon has multivariate normal distribution. And then I can ask whether, for example, y has the multivariate normal distribution. What would be the relation of the covariance of this guy to this guy, and so on. So a lot of things that we learned about in the previous lectures can be applied to this case. And this single formula is very useful to remember as the basic setup of linear regression. Okay. Any question about the derivation or the meaning of these parameters? So these have some names. So this guy is sometimes called the design matrix. And for the most part, so mostly non-random for us. In this course. You could assume it to be random later. But so this is, let's say, the coefficients, vector of coefficients. So unknown and not random. So this is the unknown vector that you're trying to estimate. So if we estimate this, so x is, this is known. So the design is known. So you know these independent covariates or independent variables or covariates. Beta is unknown. And so known. And epsilon is also, so let's say, I'll do this different color here. Non-random. Non-random. How about epsilon? What can we say about epsilon? Is it random or not?
It's random, right?
Random, yes. So we assume this to be random. Otherwise, there's no statistics. Everything would be deterministic. And is it known or unknown?
Unknown.
Unknown. So this is unknown, basically unobservable if you want. Random, so this is the difficulty. And how about y? Y is known or unknown?
Unknown, since we don't know the sigma.
No, we haven't talked about the variances, but we do observe this vector. So you observe it, so it's going to be known. You don't observe the random variable, so this is a realization of the model. So let's say you don't observe this random y here, but you observe samples from it. And this is a sample from the model. So this vector collects a sample from the model, so you actually observe this sample. There is a random vector associated with this, which is like an abstract object that we work with, but the particular realization of it we observe. So if that's helpful, so you get used to it. So this is known and random. Why it is random?
Is it because the epsilon?
Yes, in general, because of the epsilon, this is going to have to be random. Okay, so these are the pieces. So basically you observe x and y, you don't observe beta and epsilon, and you want to estimate. So the goal is to estimate. Goal is to estimate beta. Okay, that's our goal. So once I estimate beta, basically I know this linear function. See, remember this function is basically determined by beta. So I know the relation, the functional relation between the response and the independent variables. Okay, that's our job here. So any question about this? Okay, so there are a couple of assumptions that we're going to make. So we're going to assume that epsilon i's are zero mean, or have zero mean, which means that the expectation is zero. So the entries are have zero mean, or equivalent is for I equal 1 to n, or equivalent, you can say that the vector as a whole has zero mean. And then we're going to assume we're going to have two conditions. So this is going to be true always. And we're going to assume that the epsilon i's are, let's say I from 1 to n, are uncorrelated. So the covariance of epsilon I, epsilon j is 0 if I is not equal to j. And this is equivalent to saying that the covariance matrix of epsilon is diagonal. So I can write it as covariance matrix is diagonal. Actually, let me do this. So we actually assume this and furthermore assume that epsilon i's have equal variances. So variance of epsilon I is equal to the same thing, sigma squared I from 1 to n. And these two conditions together, so these two, are equivalent to saying that the covariance matrix, what can we say about the covariance matrix of sigma? Sorry, epsilon. If I know these two, how can I express these conditions in terms of the covariance matrix of sigma, epsilon? I know that they're uncorrelated. Yeah.
Will we say that they can be expressed as a multiple of identity matrix?
Right. So I was expecting like a little bit more details before we get there. That's the end result. Yeah. So the variances are sigma squared. So you get sigma squared on the diagonal. These are the variances, and all the other off diagonal elements are 0 by assumption. All the covariances are 0. So these are the off diagonal elements. So everything is 0 outside, and then you can verify that this can be written as sigma squared times the identity matrix. The identity matrix is the matrix that has 1s on the diagonal and 0 elsewhere. So you can pull the sigma squared out. So that's a compact way of stating that assumption. So this, I believe I sometimes call this E1. Let's see later. This is not standard, but assumption, let's say E1. Let's see if that's the case. Yeah, so, well, actually there's a little bit more to it. So we assume this and yeah, so we need to assume. So we assume this and as well as, so uncorrelatedness is not enough for us. We assume that epsilon i's are independent. So these pieces are independent. So this is assumption E1, that I call E1. And this is the first half, this part can be compacted written as the expectation of this vector is 0 and the covariance matrix is sigma squared IN. So that's the complexity, but then you also assume that the entries are independent. There's also E2, which is a little bit stronger. And this is assumes, sometimes you work with the assumption that, that this vector has a multivariate normal distribution with mean, which is 0, and the covariance, which is sigma squared identity. Okay, this is a very compact assumption and easy to remember. And the idea is that this assumption is in general stronger. So E2 in general is stronger than E1. Okay, some of the results that we talked about only need E1, and in fact, some of them only need the first two p's, just that the mean is 0 and the covariance sigma squared IN. But sometimes we need the independence as well. Some of the results, especially about the distribution of random variables, when we want to talk about the distribution of random variables, we need some assumption about the distribution of epsilon, more than just the E1, and this is our assumption in that case. So this is our stronger assumption, let's say. So what I want to say now is, so by this I mean that is basically E2. If you know E2, then E1 has to hold, but not vice versa. So E2 is stronger, it implies E1, but not vice versa. So why does E2 imply E1? If you remember the discussions that we had just earlier, why can I conclude from this that all these hold?
Well, is it because from the first that we know that the mean is 0, and
yeah, the mean is, right, the mean is 0 because the mean is given here. Okay, then what?
Then we know that the sigma square identity, since it's multivariate normal and the covariance is 0 in the identities, we can also say that it's uncorrelated.
Yes, so that's basically what we argued here. So this part gives you the covariance of sigma squared IN, so they're uncorrelated and the equivariance, yes? How about this part? Why this is true?
Because it's given the, it's MVN, and
yes,
covariance equals 0 means that it's also independent, right?
Yes, so that's exactly it. So because we're in the multivariate normal family, and we're assuming that all the covariances are 0, so all the entries of this are independent. Because in the MVN family, independence is equivalent to uncorrelated. So that's the fourth property that we just talked about today. So this condition implies E1, but in general, E1 does not imply E2 because you could have multiple distributions, not necessarily multivariate normal, that satisfy E1. So you could have 0 mean covariance like this. The entries could be independent, but jointly they don't have multivariate normal distribution. Let's say you could have examples of that. Okay, does that sound good? So these are the assumptions on the noise. Okay, so I have some time to talk about assumptions on X. So assumptions on the noise are clear. So this is the first set of, so these are basically assumptions about the randomness in the model. There is one piece of assumption about the design that we need to make. Okay, and let's see if I can make an extra page here. Okay, it did not work. Unfortunately, delete this page. try here. See if I can get a page here. No, that's not what I want. Okay, get a page here. So this leftover from previous lectures. Ignore. Okay, so this is leftover. So now assumptions about X. So before getting to that, I have to mention that we usually, so this used, I've written that this is n by p. We usually add a column of one, all ones, one vector. So it's a vector which has all the entries equal to 1 in Rn to the design matrix. Design matrix. So what I would have is 1 x1 transpose 2. Sorry, let me not do it like that. Yes, I would have 1, 1, 1, and then the rest of the covariates go here. Right, so that would be my x. So anyone knows why we do this often? Add a column of all ones. So I would have yeah, I'll need some more notation, but there's some unfortunate notational. Okay.
Is it because then we can add the epsilon?
No, we don't want to add the epsilon. We want to do something else. So these guys. So let me. So let's see what is a good way of describing. So one of the issues is that I use this notation, x1 up to xn, to refer to the rows of x. Now I need to change. So this is a warning. Unfortunately, need to change the notation. Change notation about xi. So, or xj. So from now on, let xj, this vector, denote the jth column of x. Instead of xi transpose being the ith row, I'm going to use this to denote the jth column. So x would have, let's say, column x1, column x2, column x p, and I have another page here. Sorry. Okay, so once we have this, if you write y is equal to x theta plus epsilon, then you can verify that this is equivalent. So this part basically is equivalent to saying, when I multiply this, say x1, x2, xp. If you go back to the linear algebra discussions, there is a compact way of writing this multiplication. Do you remember? If you represent these columns of x as x1, x2 up to xp, basically x beta has a particular representation in terms of these columns.
Would it be the summation of xi bi?
Yes, exactly. I'm going to use j to be consistent with the column notation. Just it's a dummy variable, it doesn't matter. So j from 1 to p. Yeah, so it's just going to be exactly a linear combination of the columns with beta being the coefficient. So what I would get here is that y is equal to summation j from 1 to p xj beta j plus epsilon, or if you want, y is beta 1 x1 basically plus beta 2 x2 plus beta p xp plus epsilon. That's another way of representing this. So these are vectors and columns. So adding a column of 1 to x, and let's say beta 0 to beta, what we do is we write x beta, we add a column of all 1 here, and then I have x1 here, xp. And then I also have a beta 0 here, and now beta 1 up to beta p. So now my beta would be this whole thing, my x would be this whole thing. And if I multiply out, I get beta 0 times the column all 1, beta 1 times the x1, and so on. So I managed to get the column of all 1s. And if you now write so y would be basically beta 0, yeah, a little bit of time, sorry. I'm going a little bit over time. Let's just finish this, xp plus epsilon. And then if you write the elements, individual elements with I equal, the ith element of this is just always going to be beta, because it's a column of all 1s. And it's going to be beta 1 x, right, y I1. This is the first, the covariate of the ith subject, xip plus epsilon. So this is equivalently adding an intercept into the model. That's what this is doing. So adding a covariate of all 1 just effectively puts a constant parameter here, which is the intercept. So add an intercept parameter. Basically, instead of assuming this function to be linear, we are assuming it to be affine in the covariates. Because if you remember, this part is linear. Sorry, this part is linear, and we introduce an extra constant here, which makes it a constant shift, which makes the function affine. So by including the constant in the design, we're effectively assuming y is an affine function of the covariates rather than linear. And it's just a simple extension that helps later developments. Okay, so we ran out of time, sorry. But for the next time, please go over. So we almost talked about most of the preliminary ideas. I talked about the constant 1 here. And it talked about the assumptions. The only thing that we are left with is the assumptions on x1. And next time I'm going to come back and hopefully you have gone through it and we can discuss that assumption and then move on to actually estimating the parameter of interest. Okay.
Thank you, Professor.
No
Thank you,
problem.
Professor.
Okay. Thank you. No questions?
Yeah, I have a question regarding to
Yeah.
midterm. I think someone asked on Campus Wire.
Oh yes, I have to. Okay, I haven't looked at it. I'm gonna try to announce it soon.
Okay, is it gonna be anytime this week, next week?
No, it's gonna be not next week. No, not that early. So I'm gonna, we have to go through basically inference in regression, and then you'd have enough material to do a midterm. I'm gonna announce it by the end of this week. It's not gonna be next week.
Okay, thank you.
Yes.
Thank you.
Yeah, no
Thank you.
problem.
Have a nice
No
day.
problem.
Yeah,
You too.
have a good day.
Bye-bye.
Bye-bye.
You too. Bye.